Topic 10. Current of electricity. This is the last part 6. Internal resistance, symbolized by little r. Internal resistance. Copy down definition. Now, so far we have always assumed that the power source, like a battery, is ideal and has no resistance of its own. A real battery, however, has some resistance called internal resistance, internal to the battery, abbreviated small r. The resistance in the external circuit, external to the battery, is called external resistance, abbreviated capital R. This is how we should draw a real cell. This is a symbol of a cell, and in series with it is this resistor here representing the internal resistance of the cell. The symbol is small r. The cell produces EMF. The voltage produced by a cell is called EMF, symbolized by A. And a small portion of that EMF is needed to overcome the internal resistance of the cell. And that little portion of the voltage is called lost volts, because it is a loss to us. We can't use it. And what's available to us for the external circuit here is called a terminal voltage. So terminal voltage is simply equal to EMF minus lost volts. And this terminal voltage can be used by this external resistor R. This first paragraph is really a summary of what I already explained on the previous slide. Let's look at the second paragraph here. It says the lost volts is symbolized by VR, little r, or the voltage across the internal resistance, small r. And the terminal PD, or terminal voltage, is symbolized by VR, V big R, representing voltage across the external resistance, big R. And here's the equation that reads EMF is equal to the lost volts, or the voltage across the internal resistance, plus the terminal voltage, or the voltage across the external resistor. Effect of decreasing the external resistance, big R. Now the lost volts is also equal to IR, current times the internal resistance, or just simply IR. And then this equation here becomes this. Instead of writing VR, you write IR like this. But this VR can also be expressed in terms of IR like that. I times big R. Now you got a common factor I, which can be taken out, and you introduce brackets. So the total resistance of the circuit is little r plus big R, which can be represented by RT, or total resistance. Now if we reduce big R, then the total resistance must decrease. As a result, current must increase because EMF is fixed. And if current goes up, then the lost volts here must go up too, because current goes up, but the internal resistance stays the same, so the lost volts increases as a result. In other words, more voltage lost. Here is a circuit showing a cell that has internal resistance, and it is in series with an external resistor. And this graph here shows the energy level at different points along the circuit. And you can see here, as the current flows through the cell, it picks up energy. Remember, voltage is energy per coulomb of charge. So it picks up all this much energy, and as it flows through the internal resistance, some energy is used up, so energy level drops. Then as it goes through the external resistance, the rest of the energy is used up, so the energy level is at zero after going through both resistances. And then as it goes through the cell again, it picks up some more energy, and so it goes on. This example wants you to calculate the internal resistance of the battery, and you can work through it yourself, and the answers are here. This example says a 9-volt battery is short-circuited. Okay, just highlight that, short-circuited. And the potential difference across the battery is found to be 8 volts. And the current in the circuit is 5 amps. And you are to calculate the internal resistance of the battery. To give you a clue, because it's short-circuited, the battery is short-circuited, therefore there is no external load or external resistor, so big R is 0. Now that should make it easy for you. You can solve it. Effect of internal resistance on terminal voltage or terminal PD and power output. The greater the internal resistance, the greater the lost volts, as we have already seen, and the smaller the terminal voltage will be. The output power is given by this P equal to I square R. As internal resistance increases, the total resistance increases as well, as is obvious, and the current in the circuit decreases as a result, because this resistance and current are always inversely proportional to each other. As a result, the power based on the formula here must also decrease, because if current decreases, then power must also decrease.